What about something like multivariate outliers? Now, this is not something you typically talk about probably before. The idea that someone could be an outlier not just because of a single score. It's not that their score on one, they may look perfectly normal in a distribution of scores, but we take their score in combination with other scores, it may start to look sort of strange. Okay, so a subject score may not be an outlier on any single variable, but on a combination of variables, the subject is an outlier. So, for instance, being a teenager, if you're studying people, say from adolescence to adulthood, being a teenager in that sample is normal. It's fine. There's nothing wrong, nothing weird about that. Someone saying they make $50,000 a year, probably within normal range. But when you got a teenager making $50,000 a year, like someone under 18 making $50,000 a year, that's probably in combination is probably a multivariate outlier. All right, so it's looking at things together that the person stands out, doesn't quite fit because of the combination of scores. That's a multivariate outlier. We have one of the ways that we measure a multivariate outlier is something called a Mahalanobis distance. It's a measure of deviance from the centroid. So centroid is the center of multivariate space, multivariate distribution. So it's hard to picture because once you get past 3 variables, we can't even picture past 3 dimensions, right? All right, normally we're used to thinking about things sort of 2-dimensionally. I don't know if you can see this bottle. Okay, you think about two-dimensionally. We only see it. We have our planes, and we think about things 2-dimensionally. All we think about is the points going along this point here. But we also can think about things sort of, so there's X, Y, but there's also a Z coming out forward. So we also have a point that's coming out this way towards you, and it actually has you can have 3 dimensions of space going around. Beyond 3 dimensions, we can't even picture what that looks like. We have 4, 5, 10 variables. The idea is that somewhere in this thing, the space, these are all points sort of, in space going through, there's a center someplace. And regardless of how many dimensions we have, this has some center. We call that the centroid, right? Right in the middle of this thing is the centroid of things, right? So that center, so what we talk about is the centroid of multivariate space. So in this case, 3 dimensions, but it could be 4, 5, 10, 50, whatever dimensions. And that's the center. What Mahalanobis distance does is it finds the center of multivariate space, and it tracks out how far each score is away from that center, okay? Depending on the number of dimensions you have, we can then figure out it's chi-square distributed, so we can actually figure out if the chi-square value for the Mahalanobis distance is actually large or significant or not. So usually the critical value is a chi-square with degrees of freedom equal to the number of variables you're using. So if you have 5 variables, you would look up a critical value for chi-square for 5 degrees of freedom at an alpha 0.001, not 0.05 like normal, 0.001, because we're actually looking for outliers, extreme outliers. Again, that 99% or above, not at the 95% or above. Okay, this actually 99.999% or whatever. It's like 0.9% or above. Okay, so we want extreme outliers for this, and we look to see if our Mahalanobis distance value for each person, each person is going to have their own Mahalanobis distance, the combination of their multivariate outliers, and we can see if that is greater than the critical value for that chi-square distribution. And if it is, that tells us a multivariate outlier. So what do you do with the multivariate outlier? You find a multivariate outlier, there's not much you can do except delete that case, or at least deselect it for that analysis. You may not want to delete it permanently from your data set because it may be useful for something else, but in your MANOVA or some other multivariate test, they're a multivariate outlier. It's going to cause a problem, so you may want to deselect it for that analysis. We assume linearity, right? So this is a limiting yet flexible assumption. Limiting in the sense of, we want things to relate in a linear way. And that's something we're used to seeing. We're used to seeing that, we have our X and Y planes. We want things to, have some, we're going to try to fit a linear relationship between them. Okay, it's actually not very visible. There we go. We want to have some linear relationship is typically what we're doing in a simple regression. right? The assumption in most analyses, and I can show you an example of RESTran in this data set called RESTran in ARC. The idea is we actually are trying to fit a linear relationship, but it's flexible enough that we actually can manipulate that somewhat. Right. I'm going to load RESTran as a data set. Let's take a look at that one. All right, so that's the data set loaded up. I can do the same graph and fit, and just X and Y are the things are going to be put in here. They're very generic. All right, look at this. Okay, so again, we assume a linear distribution. So if we are able to put ordinary least squares, O less to 1, that's our typical linear relationship between the variables. Now, if you look at it, actually, there is a linear slope, but you can also tell something else is going on. The reason why I say that linearity is a restrictive but sort of flexible is that we can actually tweak this a little bit to account for the curve. And the way we do that is by squaring the predictor. So the predictor down here, whatever this x is, if I put in another version of it, so it's x, and then I add in x squared as a second predictor, I'm going to move ordinary least squares to 2. But this is moving it to 2 means I'm squaring the predictor. This is O less 2 means squared. Okay, I now can account pretty well for that that curvilinear effect, right? So we've now added in the regular linear effect, and by squaring them, we've added in a quadratic effect, right? Quadratic. So this is adding in, it has both the linear and quadratic prediction at the same time, and you get this nice curvilinear effect. So even though we are assuming linearity, we're assuming linear relationships, we can actually tweak it by putting in squares, adding cubes and other powers into a linear prediction to account for some curvilinear trend like this. All right, moving from linearity to another I think fun assumption is homoscedasticity. I'll say it again, homoscedasticity. It's a tricky one to say, and then if you violate it, if you don't meet homoscedasticity, you've met heteroscedasticity. So another sort of 50-cent word. You've heard of this before. You may not have known you have, but you have. Homoscedasticity is an assumption for continuous data, like in regression, but it's the same assumption that you have for homogeneity of variance. The homogeneity of variance we have in t-tests and ANOVAs, where we're assuming that the variance is equal across groups, right? So we have grouped data, we have a grouped predictor, and we're assuming that the variance is the same for each group. That's homogeneity of variance. When it's ungrouped, it's the same assumption, it's just the way that you think about it or test it is a little different. For ungrouped data, the variability for one variable is the same at all levels of another variable. Okay? There's no variance interaction. There's no variance by predictor interaction, okay? The violation is called heteroscedasticity, and I can show you an example of geese in ARC. But the idea is that you want the variability at all points to be the same. So again, that was really easy to think about when it was homogeneity variance, because our predictor was group 1, group 2, group 3. Simple. This is whatever my y is. This is my x is groups. Whatever my y is, I want the variability of points to be roughly equal across the groups. Right? So I'm assuming group 3 could be higher in mean. There could be a distribution, a pattern this way where, if I was plotting out the means of these 3, right, where, it's actually going up like this. But I'm assuming that the spread of scores for each group is roughly the same. We're going to get about the same variance in each group. That is homogeneity of variance, right? So again, because our predictor has limited value, it's actually pretty easy to look at what that might look like and be able to test it with something like a Mockley's test of, not Mockley's, Levine's test for homogeneity of variance in SPSS or other things like that. What's looking at are the variances roughly equal. All right, let's look at geese in ARC and see when you have continuous data, what does that look like? All right, so I'm gonna load up the geese data set. Okay, graph. That's going to be observer 1 versus observer 2. We can put in the linear trend. Okay. So let's explain a little bit about this data set. So what this is, sort of a goofy data set, but you get the idea of how it impacts or how it relates to homoscedasticity. So they had people go out into a field as flocks of geese flew overhead, they had each person, 2 different observers, guess how many geese were in the flock. At the same time, somebody took a photo of the geese going by, and they were able to count exactly how many geese there are to get some accuracy data. But this is just the 2 observers. And if we do this thing where we remove linear trend, we take the trend out, this sort of shows you the distribution of residuals. You can see they're all over the place. At smaller numbers, down here towards the bottom, which means you had a small, so let's say 5 geese fly by. All right, with 5 geese fly by, it's pretty easy to go 1, 2, 3, 5. The other person goes 1, 2, 3, 5. They're able to get much closer to one another whenever they're, the flocks were small. As the flocks got bigger, I mean, somewhere they had a flock. People were guessing upwards of almost 500 geese going by. They started to spread out more. You got people who are overestimating, people who are underestimating those same flocks of geese. You can see the variance down here is pretty small, but as you get farther out, it gets more and more, it gets larger and larger. Let me actually plot. Let's do observer 1 versus the photo. So this is a little bit more interesting because the photo is supposedly accurate. So this is how accurate is observer number 1 at guessing versus the photo that's supposed to have the accurate number. Okay, so down here towards the bottom, the person was pretty accurate relative to the photo, pretty tight around the photo's estimate. But as the numbers got bigger and bigger, the person started to under and overestimate more, and the variance got larger. Okay, so again, if I move linear trend, you can see the variance down here is small. So at low numbers, the variance, at low numbers of x, the variance for y is small. At high numbers, it becomes larger and larger. And the variance spreads out. You can see the sort of cone shape where it started to fan out this way. That's one way of seeing a violation of homoscedasticity, is that the data is starting to fan out, get larger, spread out more as you go to higher numbers or something like that. Another assumption for multivariate data is something called multi-linearity or singularity. And actually, the assumption is not multi-linearity, it's actually the absence. We're assuming there is no multi-linearity or singularity. What this is if correlations between 2 variables are excessive, especially like 0.95 is humongous, then this represents multi-linearity. But I would say even something 0.8 or something would be multi-linear. Tomaszek and Fidel have different levels too, but again, if the correlations start to get high, it means that predictors that you're treating sort of independently are not so independent. They actually have a lot of overlap between them. If the correlation approaches 1, then the variables are singular, meaning they're so correlated they are the same thing. Okay, so multilinearity sort of turns into singularity as it gets more extreme. Or singularity is an extreme form of multilinearity. So often multilinearity or singularity occurs in data because one variable is a near duplicate of another. This happens by accident sometimes. I've seen people do this without really thinking about it. They'll have a number of predictors that they want of an outcome, and then those predictors are also part of like a composite measure, and they'll have the individual predictors and the composite in at the same time, and that will cause them to be correlated, and you'll have some multilinearity. In a more practical sense, if you're having a bunch of predictors trying to predict an outcome, and those predictors are correlated, they're essentially, like mathematically, they're going to knock each other out of the equation anyway. So neither one of them are going to be able to contribute much independently, and they're redundant. So the higher the correlation is, the more these predictors or variables are redundant with one another, That just should tell you that, well, if they're redundant, I don't need to have them both in the model at the same time. Right? They're doing the same thing. They're trying to explain the same things in our model, so I don't need to have them in there. So that's what multi-linearity sort of tells you, is that there's some redundancy in the data. You probably don't need to have some of these variables in at the same time. If it gets bad enough, multi-linearity, or if it's present, a lot of programs, SPSS, or the packages that do some of these multivariate designs, Psych in R, and even other things like SAS or whatever, if they're trying to estimate a MANOVA or something, and you have a high level multilinearity, it sometimes won't even be able to run. You'll get an error back saying that the data matrix is singular or something, or cannot invert matrix, or a different number of errors will come up telling you that there's too much redundancy in the data set, and it can't run. It won't even do the analysis. Okay, so you want to avoid that for sure. All right, let's talk about some transformations. You're looking through your assumptions and you figure out that your data is a little skewed or not quite normally distributed, and you need to try to squeeze it into a normal distribution. Transformations are one of the ways in which you can do that. We're going to talk about transformations. The reality is, whenever you go to do a transformation, this is like a note here, or a caution. Try running the analyses with and without the transformations, and if you're getting about the same results, it's probably better to go without the transformations. It's easier to talk about. It's easier to describe. It's easier to explain. It's easier to convey to your audience. All right, so keep that in mind. I'm going to tell you what transformations are, talk about sort of how they work and what they're supposed to do. But in reality, you should try to avoid using them if you don't have to, right? Because it makes your life more complicated. There are certain things, certain fields, things like reaction time, stuff like that, that's almost always automatically transformed because of the nature of the distribution. But for the most part, if you don't have to transform, don't. Makes your life a lot easier. Now, that being said, let's talk about what transformations and what they do. And now you see what I say here, and it's a little bit, tongue-in-cheek, kind of funny or whatever, forcing that square peg in a round hole. Because reality is there's likely other kinds of models or tests or analyses that you could use that would allow for the kind of distribution you have. You may not actually have to transform. You can just use the more appropriate analysis. So we are sort of taking a distribution that's highly skewed or something like that, and we're sort of forcing it into this round hole. But that's sort of the nature of transformations. Okay? We have assumptions like normality, and even to a certain extent, things like homogeneity variance, that kind of stuff. If we can tweak the data somewhat to actually fit the assumption, assuming that the tweak is not too massive or too jarring to the data and what it is you're trying to do. So it allows for the correction for non-normality caused by skewness, kurtosis, and other problems like lack of linearity. Shouldn't be done if values represent meaningful scale. That's a tricky one. So think about that for a second. What is a meaningful scale? Most of the time, the scales we use are somewhat meaningless. The Likert scales and that kind of stuff. What's the difference between a 7-point scale or a square-rooted 7-point scale? Probably doesn't matter a whole lot. It's not super meaningful. What if the data is something like IQ or something where there are specific values that we know of, things that we're familiar with? Probably shouldn't transform, because then it's going to take away from that understanding that your audience is going to have about the scale. So scale is meaningful, probably shouldn't be done. If you have a moderate, mild to moderate violation, you can square roots. There's a log transform that's for more severe. And you can also take the inverse if you have even more severe, like a very severe violation. Well, a couple things to keep in mind is that for log transforms, for many transforms, before you transform it, you may have to adjust. For instance, if you have negative numbers, square root's not going to work so good. If you have a 0 in your scale, log 10 is not going to be great. Inverse is going to, not only is it going to squeeze your data in, it's also going to reverse the order of items so that your largest number is now going to be the smallest. You got to keep that in mind, that inverse also does sort of flip the scale. All right. And there's, in the Tabachnik and Fidel book, they have instructions on sort of how to do these things, how to shift things over, how to make sure you don't have zeros, just to move the scales around so that this stuff will work. So definitely refer to their textbook when doing any of these things. For positively skewed data, square root and log will keep data in the original order, but it'll pull the tails in, right? So if you have a very skewed data set, it's going to, bring everything in and make it, it's not going to necessarily make it normal, but it'll bring the skewness in so that it's not so large. For negatively skewed data, the reverse is true, okay? All right, so, I mean, even, again, if the skewness is negative, you have to then shift it over and make sure all the numbers are positive, even if it's in a negative direction, which state square is going to sort of squeeze everything in, okay? The inverse flips the order of the data. Whenever, so the largest values become the smallest and vice versa. Let's look at this. So here's a data set. This is the original data, unaltered, untransformed. A couple things to make note of. One, this looks like, yes, it's skewed, but there also might be an outlier here. But this is the sort of problem. It's not a problem. It's just that the skewness and outliers are going to be linked, and you have to sort of treat them both at the same time, because I could do a transformation that may bring this in and it might get rid of it as an outlier, but I can also get rid of the outlier and it might actually reduce the skewness. So you have to sort of think about it holistically between the skewness and the outliers. But look, if I'm looking at this, right? So it's got, we got the means, median modes, just basic descriptives. The thing you want to look at here is the skewness and kurtosis values. So as we said before, if we're looking at skewness and kurtosis, my z for skewness, right, is going to be that 0.978 divided by 0.141, and my z for kurtosis is going to be that 2.213 over 0.281. So let's see, what are those? I'm assuming these are not good. These are over our limits, but 0.978 divided by 0.141 equals, this is equals, 6.94. Let's just say that, 6.94. Okay. Here, 2.213 divided by 0.281. This is 7.9, nearly 8. Okay, so these values are not good. These are telling us that there's some pretty severe non-normality. Okay, we got skewness and kurtosis values both. So it means this is, homogeneous, and we also got a bit of a tail. So what do we do? Well, let's try some of these transformations and see what they do to the distribution. I included the values for the regional scale down here, and I've now gone to the data without the outlier. All right, so the first step is I took the outlier out to see how much that's going to change things. Let's look at the new values. So I have a z for skewness of 0.692 divided by 0.141. So I imagine that's going to affect that. Right, but let's look at the z for kurtosis. Looks also 0.752 over 0.281. Okay. Let's see what those are. All right, let's look at 0.692 divided by 0.141 equals. All right, so I brought it down to 4.9. Okay. What about the kurtosis? Kurtosis is now 0.752 divided by 0.281. So 2.67, 2.7. So somehow we're getting rid of that outlier. We've now sort of, this actually seems like it's okay now. It's below that 3.3. You don't have anything disconnected here. Now, again, a note: the disconnection is a little bit interesting too, because depending on how you do this, depending on how finely you cut these bins, you may create or eliminate space. This is just based on the default that comes out of SPSS. It looks like there's no more space. Okay. All right, so that's good. I'm going to leave the originals down here, and let's keep talking about how else we can take the data, because it looks like it's still, even though we did fix the problem, not fix the problem, but we got rid of the outlier, we brought the skewness down, right, 6.9 to 4.9, it's still skewed. All right, with the square root transform, right, so we took and square rooted everything in every single one, so now you notice the values are much smaller. Let's look between the two of them. 25, 50, 75, 100, these are large-ish numbers. Now, 6, 7, 8, 9, 10. Shape is the same, everything's just sort of squeezed in. It still looks a little skewed, got a little tail on that side. Let's see what it looks like now. I have, let's see, a z for skewness equals 2.380 over 0.1141. Okay. And then I have, let's just look at kurtosis anyway. 0.177 divided by 0.281. All right. What are those now? 0.380 divided by 0.141. 2.69. All right, so by simply square rooting everything, I've now brought this down to 2.7. Is under our 3.3 skewness and kurtosis rules. So let's see, 0.177 divided by 0.281 equals 0.63 or something like that. Okay, so now both of these are within an acceptable range for skewness and kurtosis, right? This is still skewed. It's just not significantly skewed. So it's sort of like normal enough. But let's look at what other kinds of transformations might do to the data. Here we got the log 10 transformation. So I just logged every single number in the original data set. So just a reminder, I logged these values, right? These numbers. I didn't take the square root and then the log. It was a log of the original data. All right, so now it's brought everything in, even though there's still a little bit of a tail here. It's almost unnoticeable because it's been pulled in so much. Our values are now tiny. Let's see where we are now. By taking the log transformation, the z for skewness equals 0.088 over 0.141. Z for kurtosis equals negative 129 over 0.281. This is now sort of reversed the kurtosis direction. Okay. See, 0.088 divided by 0.141 equals, this is now 0.08 divided by 0.141. It's roughly 0.6 now. This one, 0.129 divided by 0.281 equals negative 0.5. And these are both really small. We went from a 6.9 to a 0.6 by taking the log transformation. So if you can imagine the original z for skewness were much larger. It was much more skewed. By taking the log, it would bring it way in. It really reins it way in. The cool part is it keeps all the data in the same order. It just reduces everything down and squeezes everything in. So with the inverse transform, remember now, it sort of flips everything around. Where the largest values before are now the smallest values are now the largest. Now this is a little bit misleading because it looks like the tail's on this side, but it isn't. It looks like it's still the same shape. But we went from, back here where we had a data point of 100 up here. That 100 is now this like 0.01. Okay, so this is the same distribution, just in reverse. It pulls everything in. It definitely sort of reduces a lot of the data. Let's look at the z for skewness equals 0.45 over 0.141, and the z for kurtosis equals negative 0.083 over 0.281. Those, see what they're doing. Point 0.45 divided by 0.141 equals 3.19. Now this didn't do 3.1 as much of a impact. This is right on the borderline, but still brought it down from 6.9 to something much smaller. And let's see, 0.083 divided by 0.281. 0.083 divided by 0.281 equals 0.3 roughly, negative 0.3. Okay. So again, this is, it's brought the kurtosis in by allowing reverse it a tiny bit. It brought it in with an acceptable range for skewness, but didn't do quite as much as it did with as the log transformation. But it did transform and did bring it in. Just now everything's in reverse. So you got to keep that in mind, that anything you're predicting with this or whatever, it's going to flip. Like if you're doing regression or something, it's going to flip the slopes around because it's now in reverse order. So you got to keep that in mind with the inverse. One of the issues that we've been talking about is sort of transforming. When you have data that's trailing off or doing stuff you don't want it to do. The opposite, kind of the opposite problem, is that what if the data you have isn't complete? What if some people answered some questions, but not all of them? So instead of having extreme answers, they have no answer. How do you deal with that? For the most part, up to this point, I'm going to assume, which is always bad, but I'm going to assume that you've probably just relied on SPSS to deal with it, and the default there is something called complete cases analysis. But that's not the only way. Like we said in the previous lecture, that if you have outliers or extreme scores, well, we can just take those scores and just change them, bring them in, rein them in a little bit. We don't have to necessarily delete them or get rid of them. We can bring them in. The same is true for missing scores. They don't have to remain missing. We can either ignore them and just say, look, if we have enough data or whatever, we don't need these extra participants. But we can also maybe find a way to replace those missing scores. And that's what this whole missing value, missing cases thing here. So dealing with missing data, the staving off mortality with the magic of math. So what I mean there, oftentimes, this isn't always the case, but subject mortality oftentimes is dealing with something like dropout. And you have repeatedly measured things that the subjects stop showing up and they sort of drop out. So that's subject mortality. Sometimes, if we have some data for people, we can actually use some mathematical principles and things to take a guess at what their scores might have been had they shown up, based on their trajectories, based on lots of information. So there's lots of different ways of doing that. Some with better results than others, some with more complicated sort of properties, but we can do it, and a lot of it makes sense. It just sometimes may have some negative impacts on your data. All right, it's missing data. This is the data that should have been. You meant to collect it. The person was supposed to show up, or they did show up. They just skipped some questions. Maybe they missed a couple questions in your survey. Maybe they were supposed to come back for a follow-up and didn't, okay? There's different ways in which people could have missing data. Some people are they're more comfortable replacing or dealing with some kinds of missing data, and that's the other thing too. There are different types of missing data. Like if someone just forgets to answer a question, that's one kind of missing data. But there's also the kind of missing data where it says, if you answered yes to this question, answer these next 10 questions. Well, if you answered no, then the rest of those questions aren't missing. They're supposed to be blank because they weren't supposed to answer. So those kinds of questions we oftentimes don't make up or guess at or impute. It's the ones where they were supposed to respond and didn't. So the default in many programs for dealing with this, as I mentioned a second ago, like SPSS and I think even in R and SAS and lots of programs, the default is something called list-wise deletion, or better known as complete cases analysis. So basically, if we have 100 people and they're supposed to answer 10 questions, we're only going to analyze the people who answered all 10 questions. So if 10 people missed even one question of those 10, they're going to be left out. Okay. So this is a very simple and easy process. Let's just look, we'll just rely on those folks who gave us all the responses we wanted. It makes some logical sense. Let's just include the people who did what they were supposed to, who answered all the questions, didn't skip any, didn't miss any. But lots of times in with IRBs, right? So let's take a little diversion for a second. A lot of times with IRBs, human subject stuff, we have to allow subjects to skip questions if they don't want to answer them, right? So if questions are sensitive or something they just don't want to give you an answer for, we're supposed to allow them to skip it. So with that being said, if they're allowed to skip questions, then we shouldn't just rely on people who give all their answers, because the answers to other questions may be good. It's just they thought that question was sensitive or it's something they don't want to respond about. That also brings up the question, like, should we then be guessing at what they would have responded to? And that's a different question. There's lots of ethics involved here, but we're not, we're not trying to assign someone an answer that's permanent. We're just trying to fill in and guess at what they might be to complete a model or to retain more data that we need. But keep in mind that our human subjects almost always requires us, when using online surveys or even in person, that they're allowed to skip questions that they don't want to answer. So we got to get around that somehow. We got to figure out ways to sort of solve that problem. And data imputation and that kind of stuff is a way of getting around that and keeping more data than we would have otherwise. Okay? Complete cases analysis is interesting because it does sort of punish folks that don't respond. It's not really punishing them directly. It's just not allowing them to have a voice in the data. Their information, they're not allowed to contribute to the data anymore because they missed one question. Now, I said 10 questions a second ago. Imagine you had a 100-question survey. Person misses one question, and they're now out of the running. The more questions you have, the more likely you're going to have people with missing responses to some of those. It creates concerns like the percent of missing and the pattern, like who is missing what becomes an issue. How much missing you have for certain variables also becomes an issue, because if you have a lot of missing, you're going to be dropping a ton of your data. That's not good, especially when you went through all the trouble to collect them in the first place. You may have even, paid them to come in and do the research that you're doing. So we don't want to get rid of them. We want to keep them. It also limits generalizability, because we can only really generalize to people who answered completely. So there may be a subsection of people that actually are missing from your data you can't generalize to because they didn't want to answer a certain question. Okay. That's not good. So, this is just with three subjects and three variables going across here. Imagine this is thousands of people. These are tens, if not hundreds, of questions or variables. The chances are people are going to have missing data. So in a complete cases analysis, this person, subject number one, is the only one that's going to be retained. This one's going to be dropped, and so is that one, simply by missing one question. Okay, so complete cases or list-wise deletion is the process of only keeping, for analysis purposes, it's not like you're dumping them out of the data. It's just when you run an analysis, the only people that get retained or used in the analysis, like ANOVA or regression, are those that have complete cases. Everyone else gets deleted, okay, temporarily from the analysis. It's not like it takes that out of your data. Okay. Now, the only way that any of this stuff, even missing, even list-wise deletion, even using complete cases, the only way that that makes any sense, because again, to go back to that generalizability problem, we want to be able to generalize to people in the population that we're interested in. The only way we can ensure that we're not leaving people out and that we're not, that the missingness is not somehow a symptom or a property of subsamples in our data, is to ensure their data, the missing in our data set is something called MCAR, M-C-A-R, MCAR. MCAR stands for missing completely at random. So there is missing at random, and there's missing completely at random. Missing completely at random is the patterns of missing on any one variable is not related to any other variable. That means that the missingness, the degree of missing, is not related to any other variable in your data set. So imagine if you're asking questions about, I don't know, about sexuality, and people that are gay or lesbian or in the LGBTQ plus community, they don't want to answer those questions, so they skip them. So those questions now become related to another demographic variable in your data set. That would mean that's non-MCAR. Okay, so I have another example here too. Measures of IQ and income. Subjects below a certain level of IQ, right, the cutoff, say, for intellectual disability, may not have an income, at least not of their own. They may be, under guardian care or something like that. So their IQ level may relate to the fact that they don't respond about income and leave that variable blank. So there's a relationship between their IQ level and their income level that is now related, and that's then not MCAR. So the missingness has to be sort of random. People just skip the question or whatever. It can't be related to any other variable in the data set. That means if that's true, then your data is missing completely at random. So what can we do? I'm not going to go into it, by the way, I didn't go in a whole lot of other things. There's also MNAR, which is missing not at random. There's MAR, missing at random, which just means that it's there's certain cases where there are some dependencies, but I don't want to get too much into the weeds of that. There's lots of information out there about it, and I don't want to go there. That's just where we look at missing completely at random, and we'll even look at in the lab. We'll talk about some tests. How do we know if data are MCAR? There's a Little and Rubin's test for missing completely at random that we'll go through. And you just want to know if your data is missing completely at random. If it is, that's good news, because then you can do all kinds of stuff. Even listwise deletion is fine. You can actually do listwise deletion if your data is MCAR. If it's not, then it's questionable. All right, so what other things can we do? Well, what if we don't want to get rid of all those cases? What if we don't want to do listwise deletion? We have the missingness, we want to make sure people are being retained in our data. One solution is to do this missing value correlation matrix. So what does that mean? You're going to create a correlation matrix of complete cases for each pair of variables. And this is true for things like regression and other things too, where what they're going to do is for every pair of relationships, every time you're trying to look at a correlation between pairs of variables, you're going to use the maximum number of participants that are shared between those two variables. It uses complete cases for each pair of variables as opposed to doing listwise, which means you have to have complete cases across all the variables. It's just doing listwise for the pairs, for each pair at a time. All right, so this is something called delete cases pairwise instead of listwise. So delete cases pairwise is going to use the maximum number of participants for every pair, every correlation you might have. But that means you're going to have different ends in every case. You're going to be using potentially different subsets of your sample each time you run a correlation, each time you're looking for that relationship. So this is an approach that sort of maximizes the N for every single correlation, but it's not super useful beyond correlations and even some prediction regression. So what else can we do? If I want to use something like MANOVA or do something more complicated, this may not work very well. How do we deal with missing data? And this is one of those things, sort of like pulling in extreme values in a distribution. Imputation can sometimes make people uncomfortable. The first time you hear about this, to impute means to replace the missing data. We're actually going to take a guess, should be like an educated guess in some way or another, at what the missing value should have been or would have been had the person responded. So this first list here is sort of sometimes the simpler ways in which we do it. So one way we impute is, look, anytime there's a value missing, let's just replace that value with the mean of the variable. Makes sense, right? If the person doesn't respond, we just look at what's the mean for that variable and we replace it in that missing value. It's actually really good because it doesn't affect the mean estimation for that variable. The mean of the variable is going to be exactly the same. It does, however, reduce the variance, because every time you put a value in exactly at the mean, that value then contributes 0 to the sum of squares, to the variance that we're going to be computing. So it's going to artificially sort of squeeze the variance in, but leave the mean completely alone. That's a very simple, rudimentary way of sort of replacing data. It still gets done quite often. There's even like a button, I think in SPSS, when you're going to do stuff that just says replace with mean. It's real easy. All right, well, if you have groups, different, even demographic groups, you have men and women, you have different ethnicities, you have different nationalities, you have different groups in your data that are meaningful to whatever you're studying, you can actually take the mean of each group and replace that person's missing score on that variable with the mean for that group on that variable. Okay, it works for group data. Right? Obviously, if you don't have groups, it's not going to be work. It has a similar issue with the mean and variance, but as it affects the groups. So it's not going to change the group's means, but it will make the variances in each group sort of smaller. So if you are doing something like an ANOVA on those particular groups, then it may artificially shrink the variance down, and you may get significant results that you weren't supposed to find. So you got to be careful. So let's say you have treatment and control groups, and that's the thing you really want to compare in your ANOVA. That's probably not the groups you want to use to replace the mean. Use something like gender groups or ethnic groups or nationalities or anything else, age groups, something else to replace the mean, so it doesn't affect the comparison between treatment and control group, or whatever manipulations you've done in your study. You should not use those groups to replace the data with some other group. That way you don't sort of mix together or convolute the mean that's being replaced and the groups that you're trying to actually compare. Getting a slightly better approach is usually something like regression. So if I have a variable y and the person has a missing score on it, well, let's use variables a, b, c through x or whatever to predict variable y, and then actually replace the person's missing score with the predicted value for that person. All right, so we can actually use regression to predict the variable of interest, and use the predicted scores to replace the missing values. You can even do this iteratively. And what do I mean by that? Well, I can then put the missing values in, repredict y, get slightly adjusted slopes and things, and have a new predicted value for y, put it in, repredict y again, and keep doing that until the value that you put in, the value you get out for the prediction is the same. Okay, so you can just go through iteratively. But again, the variables you use to predict should not be part of the proposed model. If the thing you're most interested in is, does A, B, and C predict y, then you shouldn't use A, B, and C to predict the values on y, or else you're going to basically be biasing the missing values to fit perfectly into your model. So you want to use other variables to predict. Sometimes that's not possible because you may not have other variables to predict the missing values. But this is a better solution than, say, even group insert or mean insert. But there's better versions, there's better estimation procedures than that. So there's two that are much more, computationally complex. One is called the estimation maximization procedure or algorithm. It's a maximum likelihood. It's iterative. It basically uses maximum likelihood to figure out what the value is the is the value that sort of the most likely to be that person's score based on distribution of scores for that around that person, around the data. It's an algorithm. It's complex. Has two steps: the E step and the M step. It's like a whole mathematical procedure available in SPSS. I'm not going to go too much into what this means or what it does. What it does, it goes through and sort of predicts those scores, finds the values that it finds sort of maximum, and actually reports back to you even a standard error, like basically like a distribution around that missing value, so you can get an idea of what the error variability is. Sort of adds in some error to the replacement, so it's not perfect. Multiple imputations sort of the same, name given to a family or processes that typically use multiple estimation methods. You can put on some distributional constraints, has some built-in error estimation. It's basically like the regression, something like using an iterative process with regression. But instead of predicting one score, instead of saying like Y predicted based on some values, like, A plus B plus C, like it actually predicts a distribution of what Y predicted could look like with some degree of variability, right? Creates like a distribution of what the values could be for that missing score, and then it'll go through and randomly pick a score. With SPSS, it'll actually do this multiple times, so you can actually tell it, hey, I want to impute the missing data, and I want to do that 10 times. And then I'm going to randomly pick one of those times. So what it'll do, it'll have your original data set. It'll then create imputed data set 1, imputed data set 2, all the way down through however many you say. Let's say you say 10. It's going to create 10 imputed data sets where every missing value has been a random choice out of a distribution of possible values for your missing value, okay? Based on regression, based on some distributional constraints you put on it, like, hey, the maximum is 7, the minimum is 1, if it's like a Likert scale, all that kind of stuff. And then you're going to say, hey, I'm going to randomly pick, I'm going to pick out from here the fifth one. So I added in another level of randomness, because these have all been randomly generated to replace the missing values. All the values that aren't missing remain unchanged. Okay, it's just the missing values have been replaced randomly from a distribution of possible scores with some built-in error. And then you're saying, hey, the data set I'm going to use is going to be, data set number 5, and that's the one you use, and it has those missing values in it. Right, so you're adding in some randomness and some iterative process to your data imputation, so it actually builds in some error, and it's not just overfitting your data with perfectly fitting estimates like this. If I just plug in the predicted value, okay. And of course, we'll look at this in SPSS. It's actually a pretty cool process. It gives you multiple data sets. You just choose one that you want, and hopefully, again, you should choose it randomly and add a random process in there, and then you use that data set then, and it has all the data replaced.